Hello and welcome to Lesson 3 of Networking Fundamentals. Lesson 3, we are going to go through routing. And as you see from the content, most of the content is based on static routing and static routing deep dive, followed by the routing types, and again, a little bit stretch on static routing. We are also going to have a look into the dynamic routing and followed by OSPF, a deep dive into that, and followed by 2 labs on OSPF. Now in the routing, like I said, most of the content of the CCNA will be again taken forward in CCNP with deeper dives. But here the lesson 3 of routing is completely in scope with the new latest CCNA syllabus, which is 200-301. So let's go ahead and enjoy. Welcome to Routing Labs. So in the first routing lab, we are going to go through the routing fundamentals, followed by static routing. And in the subsequent labs, we are going to go with the process of the packet flow in the routing, and then followed by the routing protocols such as OSPF and so on. So let's first of all understand what exactly is routing. So let me go ahead and pull up some routers here. Let me pull 2 of them, 29 series. And let me also pull up some switches. Let's keep it here, 2 of them. And finally, let's go for the laptops. Let me take 2 of them for each switch for better understanding. And let's now have the connectivity done. So from switch to laptop 1, to laptop 2, 3, 4, finally routers to switches, and finally connection from router to router. Okay, so that's the topology that we are going to focus on. Let me just go ahead and remove the bottom toolbar. Okay, let me just zoom this up. All right, so now let's give some IP address here. Let me go ahead and give this as 10.1.1.1, and this one is 10.1.1.2. This is 20.1.1.1, and I will keep the mask as 24, and here also 20.1.1.2/24. Let me just indicate the subnet mask here as well, and in this one as well. Okay. Now, let's assume that we have got these 2 branch offices, okay? The office on the left-hand side, it's, let's say, on Bangalore. We have got this switch and 2 clients there. And there is one office at Hyderabad, which are having, which is having a switch and 2 connections of the laptops there. Okay. Now, between the branch offices, we have got the connectivity through switch and finally to router, right? Now here, let's say that your 10.1 wants to connect to 20.1. Okay. Now what's going to happen? Once you type the ping command to ping space 10.1, ping space 20.1.1.1 from 10.1, will it work? The first thing that it will check is that it's a different network. It is not in the same network, because if I want to ping from 10.1 to 10.2, it's simple. It will go to the switch and get it done, right? Because switch will be communicating through the LAN, through the local network. But when I'm going to a different network, then the particular 10.1 will be connecting through the router and then going through the second hop, I mean the first hop, and then finally coming to 20.1. Now, that is the job of the router, to connect to different networks. Now, the router is a layer 3 device which supports multiple broadcast domain, which basically means that multiple interfaces of the router can be connected to multiple networks. And that's how the router will be supporting multiple networks through its multiple interfaces. So in this case, this particular 10.1 will be connecting to this router. And we have got something here called, if you look into the router, we have got two interfaces here. One is gig 0/0 and one is gig 0/1. Similarly, on this side as well, it's gig 0/1 and gig 0/0, right? Now, in the gig 0/0, we need to configure a particular IP that's called the router IP that should be identified by this laptop. So basically, once you say ping space 10.1.1, the ping command or the laptop should know that, okay, fine, this is not a part of my network, like ping dot or ping space 20.1.1, this is not a part of my network. Then I should be going to the router IP to find out where that network is. Okay, and that router IP which is being stored in this laptop is called the default gateway. Okay, so let me just clear the concept of default gateway here. So let's say your 10.1.1.1/24. Now this will be having 256 IPs, right? Which means that it will start from 10.1.1.0 and keep on going till 10.1.1.255. Correct? Now, this 1.0 will be used for the network ID to identify the network, right? And this 1.255 will be used for the broadcast ID. So basically, you will not be able to use the 1.0 and 1.255. So the last workable IP will be 10.1.1.254. And that last workable IP will be used as your default gateway in the network. So default gateway should be thought about as something, let's say that you want to traverse to a different network. Let's say from from your house to the outside main street. Now, if you want to go out of your house and get into the outside first main street, your first thing that you have to do is that come out of your house, which means that you have to open the main gate of your house and then step out, right? That main gate is called the default gateway. Your house will be the local LAN. Okay, you open the default gateway and you step out, and then you go to the main street, which is the external network. All right. So in this case, your default gateway will be 10.1.254 because we are putting the subnet mask /2/24. All right. Now let me go ahead and let me type in the IP address here. One second. Yeah. So this gig 0/0 will be 10.1.1.254, right? That is the default gateway. Similarly, on this side, it will be 20.1.1.254, right? And when it comes to gig 01, let me give ID here. A network with 1.1.1.1/24, and we can say this will be 1.1.1.2/24. So these are the interfaces to which these routers are connected. Now, if you note carefully, let me just quickly take a annotation here. If you note carefully, then you will see that the router 1, the left hand side one, is actually connected to two networks. Why? Because see, if I just take this, it is 10.1.1.0, right? And the other network will be 1.1.1.0, which is connected through gig 0/1. Similarly, your router 2 will be connected to 20.1.1.0, that is this side, and it will also be connected to 1.1.1.0/24. Okay, so basically your routers 1 and 2 are connected to two different networks. Okay, so till now I hope that the concept of the routing is clear, and the router will be working in the fashion of it will store a routing table on which it will find out how to go to the next network. Okay, now on this one, a few more things here. So first of all, if you look at your PC, we have seen that the PC will store the PC will be storing the ARP table, right? This is the ARP table stored in the PC, and your switch will be storing the MAC table, right? And your router will be storing the ARP table and also the routing table. Okay, both the routers, right? So basically that means that if you look into a laptop, then your your life of the ARP table is 4 hours, and your life of the MAC table is close to 5 minutes. So basically the switches will be very chatty. Every 5 minutes post, they will again send out the hello packets, and they will again update their MAC table. And the ARP table will stay for a long time, like 5 hours. The routing table do not have any lifespan as such. It will stay for a very, very long time. Okay, so that is how the tables are being stored. And when we come to the flow of packets, then I will show you how the packet flow is happening in this network. Let me go ahead and remove all these annotations. Okay, now first thing first, we are going to configure the routers. Okay, so what I will do here is that I will ensure that in this interface gig 0/1, this network and the subnet mask are added, and in gigs 0/0, this particular IP and the subnet mask is added. That is how you add the network information or load the network information into the routers. Okay, so let me go for router 1. And the iOS, the command line will be same like a switch itself. It's only that for the router, the commands will be different and will be working here. So config T, and the first thing first which I would like to do is that change the host name to R1. Okay, then I will say I will go to the interface gig, okay, 0/0. That's the one, right? And what is here happening? 10.1.1.254, right? Press enter, and I will say IP address 10.1.1.254 space and question mark. It is asking for the subnet mask, which is 255.255.255.0. Press enter. Now, after you load the IP address into the router, you have to give a very important command that's called no shutdown, which means the link will be up. The link status is set to up, and if you look into the diagram, see now it's green in color. Link is up, right? And similarly, I have to go for interface gig 0/1, and which is having 1.1.1./25, 24. IP address 1.1.1.1 255.255.255.0. Press enter and say no shut, and we are done, right? But still, if you if you look into the diagram or the topology, you will see this link is showing amber. Why? Because this particular link is connected to both R1 and R2, and in the R2 we have not configured the network yet. The link is down there. So let's go to R2 and no, enable config T, and we will say host name first of all, R2. Then we'll say interface gig. Let me just take this one, gig 0/1, and it is IP address 1.1.1.2 and subnet is 255.255.255.0. Press enter and say no shut. Once you press enter, immediately you see this link is up. Okay. And now I'm going to go to interface gig 0/0 IP address 20.1.1.254 255.255.255.0. Okay, fine. Enter, and then you say no shut, and this link is up as well. Okay. Now, how do I check the routing table? What is being assigned to the routers? Well, there is a very simple command to check the routing table, and that command is, you can say show, okay, IP route connections, and you will see that both these networks are showing up as directly connected. So 1.1.1.0 and 10.1.1.0 are connected through gig 1 and 0, and it's showing the network here. If you look into this 1.1.1.0, it's showing clearly. So the complete network of 1 and 10, they both are connected to the R1. Okay. Now similarly, I will check in router 2 that if the interfaces are connected, and you can check it from here as well. You will say do show IP route connections, and you will see the connections are showing up properly here, right? 1 and 20. Cool. Now let's see, will the router 2 be able to ping router 1? So let's see, do ping, and I will say 10.1.1. Let's start with 254. Okay, like can this particular router ping the 254, which is right here, gig 00. Okay, press enter, and you will see that the ping will not happen. Okay, the ping fails. So why the ping fails? The reason is that to this router, it knows the network 1 and network 10, right? And let me quickly, yeah. So to this router, it knows the network 1 and the network 10. And the router 2, it knows the network 1 and the network 20. But does the router 2 know about the router, I mean, the network 10? No. Does the router R1 know about the network 20? No, right? So that's when you have to make sure that you are configuring the router in such a way that they know that network. Now, how do I do that? Now, here comes the first very simplest way of configuring the routing table so that your route can be reached. And that's a manual way, and that's called static routing. Okay, so we will do the static routing right now. What I'm going to do is that I will be loading the static route command in R1 and R2, and then we will check. And what is the command? Let's see. Easy command is just a one single line, command there. So let me go for config T. And static routing, the command is you start with IP route, and then you say to which destination network and destination subnet mask. So I want to go from R1, I would like to go to 20, right? So from R1, if I want to go to 20, then I will say 20.1.1.0. That's a network, right? And the subnet mask is 255.255.255.0. Space, and then also I have to mention what is the next hop through which I will be going to 20. So let's say standing at R1, if I want to go to R20, so this is my R1, and if I want to go to the network, 20 here, my next hop will be this guy, right? Because I have to go straight in this path and hit this particular next hop, which is 1.1.1.2. And from here, I will be directed to 20. So the static route, the command is IP route, destination, network, and subnet mask, and the next hop as well. So let me go there and type that same command in in R1. The next hop is for R1, 1.1.1.2. And we are done with this command. Press enter, right? Similarly, I will come to R2, and from R2, you will see that if I want to go to network 10, then my next hop will be 1.1.1.1. So let me go to R2, and I will say IP route 10.1.1.0 because that's the network I want to reach. Subnet mask. And my next hop is what? From R2, 1.1.1.1, right? Press enter and your command is taken. Now let's check if the ping works from R2 to R1. Okay, so do ping, and I will just check the default gateway. I will say 10.1.1.254. I'm checking this particular link, this particular point here, interface right here from R2. Let's press enter, see what's going on. And it pings, right? It pings absolutely fine. Similarly, if I go to R1 and I will try to ping, do ping 10. From R1 it will be 20.1.1.254. Press enter and it's pinging, which means that now my routers, the interfaces are connected. You don't really have to now connect the laptops and check it, because if you know that your interfaces are able to connect, be 100% sure that if you connect the devices there, they will also be able to connect. Okay. But still, if you want to connect them, then you just have to go to this laptop, let's say, and you have to configure the IP address because we have not enabled the DHCP here. So this will be 10.1.1.1, and the subnet mask will be 255.255.255.0. The default gateway will be 10.1.1.254. And similarly, in the 20 also, I will enable the same thing. Go to 20 and say 20.1.1.1, subnet mask 255.255.0, and default gateway will be 20.1.1.254. Right. Now let's see if I can connect. Command prompt ping 20.1.1.1, right? Let's see if it's working or not. And it works fine, right? You see the replies coming up. Works absolutely fine. So that is how the routers work. And what we have done right now is the static routing. Now, a couple of things I want to show you. So once I go to this particular router, now if I say that do show IP route connected, okay, you will still see the routes which are directly connected. The C actually means directly connected. Okay. Now the static route is not showing, so I have to type in the command called do show IP route. If I just type in static, it will be showing me the static route. And this is the static route. So to router 1, the static route is 20. I'm telling it via 1.1.2 because 1.1.2 is my next hop through which I have to jump to go to 20.1.110. And what is this thing? 1/0. Okay. So that 1/0, we are going to talk about in detail, but I will just show it to you later, like right now. Let me just pull a text box. Now that is basically called your AD, or what we call administrative distance. Okay. Now remember, for connected, like directly connected networks, your AD will be 0. Okay. AD is always preferred to be the least one. Like it's a 8-bit kind of concept, 0 to 255, and the least you go into AD, the more it is preferred in the routing. Okay, so for directly connected it is 0. For static, AD is 1, which is showing right now here 1. Okay, and if you go for a routing protocol, let's say OSPF, which is a dynamic routing protocol, then you will see the AD will be 110. Okay, we'll come to that in detail later on, but right now just know that administrative distance is a concept through which your routing will be preferred, and the least the AD is, the more the preference of that AD will be. Okay, so directly connected 0, static is 1, OSPF is 110. All right, let me just get into this one and clear all this. Okay, so that's about your static routing on this side. If I go to your R2, there also, let's see how the static routing is shown. Do show IP route and static, right? Okay, and you will see right here, your 10 is connected to R2 through 1.1.1.1, which is your next hop to jump into 10.1.1.0, and your AD, since it's a static, it will be 1. Okay, so that's all about the fundamentals of routing and the static routing. See you in the next routing lab. Thanks for watching. Cheers. All right, so let's start off with our routing fundamentals lab 2. Now this one will be a deep dive into the packet flow for static routing. This is one of the important labs. So let me just quickly pull up some routers. Okay, and go ahead and get some switches. And finally get some laptops. I'll probably have only one. This is similar to the last lab topology. So I'll keep only one laptop here, and let's have the connectivity done from laptop to switch. And then from this laptop to this switch. Finally, switch to router. And router to router. Okay. Now that is the topology we'll be working on. And let me just bring this here. Okay, let me zoom this. more. Okay. All right. So what we are going to do is that we will give this laptop IP address 10.1.1.1 and subnet mask will be 24. The default gateway will be, of course, 10.111.11.254. And this one we will give it 20.1.1.1/24. Okay. Now let me just pull in the default gateways as well. So here I go. 10.1.1.1. I will give it 255.255.255.0 since it's 24 subnet mask, and default gateway I will give 10.1.1.254. Okay. Similarly, I go to this laptop and I will give it 20.1.1.1. Let's give it 255.255.255.0, and this one will be 20.1.1.254. Okay, so these laptops are configured. Now, when I go to the laptops, let me just also check quickly what is in the ARP table. Before that, just once more, here, each of the laptops, okay, let me pull up the annotation here. Okay, each of the laptops, okay, they will be having a ARP table, right? And your switch will be having a MAC table. And remember that when we are talking about the router, then each of the interface in the router will be having an ARP table. Like your gig 00 will be having an ARP table. Your gig 01 will be having an ARP table. Why? Because these are the points where the networks are changing. Now this one is your 10 network, this is your 20 network, and this will be like something else, which I'm going to put right now. So your every interface of the router will be having a ARP table here, right? Apart from that, the router will also maintain a routing table. Okay. Now remember that for the ARP table in the laptop, the lifetime is 4 hours, and the CAM table or the MAC table in the switch, the lifetime is 5 minutes. Okay. So with that in mind, let me go ahead and drop here some IP address for the laptop interface. So gig 00, we know that it will be the default gateway, which we have done in the previous lab, 10.1.1.254. And similarly, I will give it 20.1.1.254. Right? And let me just pull it on this side. Here it is. And here it is. Okay. Now gig 01, I will keep it similar to the past topology, that is 1.1.1, okay, /24, and this will be 1.1.1.2/24. Okay. Now we have to give some MAC address, because like I said, we are going to check the ping command from 10.1 to 20.1 and see how the packet flow happens. If I want to check the packet flow between 10.1 to 20.1 in a ping command, then I have to ensure that we are having the MAC address, because we are going to work on the ICMP and the ARP, right? Now we do have got the MAC address, so we'll just try to make it simple here to make it show in a nicer way. So let me go to config and settings, fast Ethernet, and this MAC address I will make it 4 A's. Okay, 1, 2, 3, 4, just to have the easiness when we check them in the packet tracer. And this one also, I will leave it for now. I will not make it B, because I think I should be going in a clockwise fashion. So I will keep the MAC address here all A's. So let me just put the MAC address here, which is A. Let me just write it like that. Now, or let me just keep like 1A here. Okay, just for the clarity, we will not try to keep. We'll just think it is one single A. Okay. Now, similarly, your MAC address in the gig 00, that will be right? Similarly, your MAC address in the gig01, that will be C. Your gig01 here will be D. Your gig00 here in this side will be E. And finally, your this laptop will be having the MAC address, which is F. Now I can change the MAC address here. I can go straight away and go to configurations, config, fast Ethernet, and change it to F. I'm doing this to make sure that once we see the packets in the simulation, it will be easy for us to know that which is the source IP and source MAC, and the destination IP and the destination MAC. So this is A, B, C, D, E, F in a clockwise fashion going. Now the one more point is that the routers, I have to change the MAC address. Now before I do that, okay, I will just finish off the MAC address part, CLI, and say no, return, enable config T. I will give the host name R1. Okay. Now I need to get into the interface to find out the MAC address, like gig00. So I will say do show interface, okay, gig0/0. And once you see that, you will see this particular details, and here you will find the MAC address. Now what I'm going to do here is something which I strictly not recommend you to do that. Changing the MAC address in the router is something which you should never do. But this is something which I'm doing for the simulation just to make sure that you understand the packet flow. Okay, so I'll copy this, and gig00 we have taken. So let me go down. Okay, and what we said that we are going to make it B, right? Gig00. So I will do one thing. I will enter gig0/0, and I will type in MAC address, and this is the MAC address that we have got, um, uh, which is this one, and I will make it B. So all B's, BB, BB. Okay, press enter, and it's done. You can just check it up, do show interface, and you will see that the last four letters got changed to B. Okay, try this out in a simulation, but never on a real router, right? It's not recommended to change it. Okay, the second part is gig01. So I will just go to do show interface gig01, and let me see the MAC address here, which is this one. Copy this, and let me go to interface gig01. I will say MAC address. Okay, and paste this, and this will be C, right? That is the MAC address that we have defined here, C. So let's make it C. Enter, and we can actually check that. Do show gig01, and you will see the MAC addresses came to C. Okay, so that's about this one. The other part is that we have to configure this router now, right? So let me just give move this say from here. Yeah. Okay. Now to configure the router, we can actually go to interface gig00, then any interface gig01, and give the IP address, no shut, and all that, right? There is one more way in which we can configure the routers. It's an easier way. You can just type in the commands in a notepad, and from there you can just copy paste the commands. Why we say it's easy from a notepad? Because if you're having a good amount of devices and good amount of interfaces, then from the notepad it's easy to copy paste and just change the IP address and do it faster. I'll show it to you right now. So let me open the notepad, and what we're trying to do is that we will get into config terminal. Okay, config T, and let's say our interface. First of all, I will enter gig0/0, right? The first one, and I will say IP address. What is IP address? 10.1.1.254, right? And I will say 255.255.255.0, and I will say no shut. Correct. Similarly, I will say interface gig0/1, and I will say IP address. This is 1.1.1.1, and I will say 255.255.255.0, and no shut. Okay, so no shut. Okay, Just make sure that your command, the typo is correct throughout, and you just have to copy this command, go to your router, and you can just go back to any of the interface or just click from your typing exit and paste this, and it should be coming up, and it's done actually. So now if I go ahead and if I check do show IP interface or do show IP route, sorry, do show IP route connected, you will see right now it's 1, just 10, because the other link is 1, which is connected to the router 2 as well, which is not yet turned up, right? So 1 is showing up. The moment we turn up the router 2, that also will be showing up. Let me pull this up a little bit. Okay. So that's about the configuration done. One more thing I have to do, I have to also make sure that the static routing is configured. And for that, we know the commands. What is that? IP route. And then we will say from R1, we are trying to go into 20.1.1.0. And I will say 255.255.255.0. And what is the next stop? 1.1.1.2, right? That is from R1. Press enter and we are done. Okay. If I want to check that, I will say do show IP route static. It is not showing up now because the router 2 is not turned up yet. So let me go to router 2 and we will change the MAC address there as well. So no and enable. Okay. Now for the MAC address, we will say do show interface gig 0/0. Press enter and you will see the MAC right here. Take it up, copy that, and let's go to interface gig 0/0, then say MAC address, and then let's paste this, and we'll change this to what? Gig 00 is E, right? So you will make it E. Press enter. We are done. If you go to do show, it will be showing the all E's. Cool. Now let's go to do show interface gig 0/1. Enter, and we will see this particular MAC address. Copy that. Okay, and we will again go to interface gig 0/1. We'll say MAC address, and we will paste this. Take off the last piece, and we will say D. That is gig 0/1. Right. Enter. You can verify this. Do show, and it's coming to D. Cool. Now we are going to configure this particular router. And for that, we don't have to type in all the commands. Just go to your notepad and change it now. Your gig 00 is having 20.1.1.254. So you will change that 20 to 10 to 20, and gig 01 is having 1.1.1.2, right? And remaining all will remain same. That's the beauty of having the commands on the notepad, so that you can just copy and paste. Okay. So router 2, and you can just say paste, and we are done. If you want to check on that, yes, do show IP route connected, and you will see both are showing up here. And I will be setting up the static route here as well, which is IP route, and then I have to go to 10, right? So 10.1.1.0, and I will say 255.255.255.0. And what is the next stop for me? 1.1.1.1. Done. Now, if I want to check this, I can immediately check that. I will say static, and it will be showing up. Right. Similarly, if I go to my router 1, you will be seeing it here. Do show static showing up, and do show connected. Both of them are showing up fine. Okay, so all is configured now. Now we are ready for the simulation. So let me quickly open up the simulation here. Take off all these protocols. Just go for the ICMP and the ARP, because if you remember, those are the only two that will work with ping. Okay. Now, before I start the simulation, let me just give you a rehash here. Number one is that your in the ICMP in a packet, your source IP and the destination IP will never change. Your source IP, like if I want to ping from 10 to 20, your source IP will always be 20.1 and your destination IP will always be 20.1 throughout the flow. Okay, so 10.1 and 20.1. But all the layer 2 info will keep on changing, which means your ARP table will keep on getting updated, right? Now, let me just close this. I will show you what is the status of ARP here. If I go to this laptop, let me check. I will say ARP-A, right? No ARP entries, which means it's blank. From the router, let me quickly check on this. I think it's interface G00. I will say do show ARP. Yeah. So here also I'm seeing that yes, my C and B are showing. Basically, my C is here. This interface and the B, both the directly connected are showing up here. Okay. But that's about it. We are not having the complete address, like the C and B is showing, but we are not having the D or the E here, or the D or the A here. Okay, so the point here is that once we start the packet flow, you will see that your ICMP will fail always in the entry point of the routers, because it will not know the destination MAC in the next network. And again it will start off from here, it will fail here, and again your ARP will start from here again. So 3 times the ARP will happen basically. So let me just point out the networks here, which are the networks that we are having. We are having 3 networks here. Let me put it here. So your first network is this one, which is right here. Okay, that's your first network. Your second one is this one, that is right here. Okay, and your third one is on the top, which is this one. Okay, all right. So these 3 are the networks that we are having. Now you will see that once we start the packet flow, your ICMP will always fail near this, and again it will restart because your ARP has to go to the next network and then get the destination MAC and give it back to the ICMP, and again the process will restart. Okay, so let's have a check. Okay, instead of talking about what's going to happen in the simulation, let's have a check what's actually happening in the simulation. So I have taken ARP and the ICMP, and now I will go back to my laptop and I will start my command, which is ping 20.1.1.1. That's right, right? And press enter. Now, once I press enter, you will see immediately the ARP has failed. The ARP is the red packet, and I'm sorry, the ICMP is the red packet, which has failed, and the ARP has started off. So ICMP, if you go there and if you see why it has got failed, because in the ICMP, the layer 2 information is missing, right? And more than that, let me just pull it up here. You will see the layer 2 info. It is completely missing. So ICMP will not know actually that how to go to the destination, because the complete MAC address is not there. And let me take it off. And you will also see that if I go into the outbound PDUs, let me just take off this annotation thing here. Probably you will be having a difficulty in seeing this. If you look into the PDUs there, you will actually find that in the PDUs, we do not have the Ethernet frame. We are only having the IP header and the ICMP. Okay, so that's why the ICMP is failing. It's telling that I do not know, because the ICMP has to go from 10.1 to 20.1, and it's not knowing the destination MAC address. Here comes the rescue ARP. Okay, so one ARP request is sent out. In the request, we all know that uh, your source MAC address is A, which is the laptop. Your destination MAC is all Fs, because we all know that the request ARP is always a broadcast, right? And your source IP is 10.1, but your destination IP is 10.1.254. So your destination IP, so remember one thing, ARP will not work across the networks. Okay, ARP is a layer 2.5 protocol. It will be working in the network itself. It will not go beyond the network. What it means is that for the ARP, this is your default gateway to the 10.1.1.254, and ARP knows that this destination MAC address has to be known. Okay, I mean this particular destination MAC address has to be known because that is the default gateway. Then only my ICMP will be able to find out that what is the next hop, right? Again, in the outbound PDUs, you will see that in the ARP, your source MAC is A, of course, your source IP is 10.1, your destination MAC is all 0, which I said in the first ping deep dive as well, that this will be 0, but your Ethernet frame is actually doing that that complete broadcast, all Fs, and your target IP is 10.1.254. Cool. Now let's go to the next step. What's happening now? Your ARP request will be going. You see that? It's gone to the switch. Fine. And the moment it is going to the switch, again, the switch will be populating its MAC table, right? Because if the switch knows that, okay, fine, now for the 10.1, the MAC address is A, right? Then again, I will be going to the next step. I will be getting to the 10.1.1254. Now let's see what's happening. Once it reaches, then immediately your ARP request will be coming, because this ARP was a broadcast, right? So that broadcast was sent to the switch, and from the switch, actually all the ports which were connected to all the other PCs, the switch would have sent the broadcast to all, and the switch would have broadcasted that to this particular router interface as well. Now remember once again that every interface of the router will be having a separate ARP table. Okay, so in interface gig 0/0, we have got the MAC address B, which we said, and there the ARP has reached. Now let's see how does it look like. You will see the inbound and the outbound here basically. So before that, it's coming from B. Okay, the destination is B actually. The destination is B, and it is going back to A. That is the response ARP. Okay, and the request was, it was coming from A and throwing a broadcast. So A to broadcast was the inbound or the input, and the output is from B to back to A. Cool. These are the inbound PDU details, and this is the outbound PDU details. Okay. Now let's see. Now your ARP is coming back, and it will give the information back to the 10.1 that, hey, now the 10.1 actually knows that, okay, now my destination MAC for this gig 00 10.1.12 we know that MAC ID. That MAC ID is B, which is here, right? Now, with the help of this, now the ICMP request will again be thrown. Okay, because the ICMP initially was not knowing the destination MAC address. It was not knowing the path in the layer 2. Now it knows that. So let's see how it works. If I click on this, it's having the layer 2 info, which is from A, it has to go to B. Okay, so till the 10.1.254, the ICMP knows like where to hit. And your outbound is showing all the same. One more thing you keep a check on this is that the TTL is showing 128 here. Now you will see slowly that TTL will change. Okay, 128, all fine, all good. Now let's go to the next one. So your ICMP request has gone to the switch. It goes to this particular source. Okay, and then it fails again, and then again your ARP starts. Okay, now remember, your ARP will start from the point from where it failed. Okay, but your ICMP will start always from this source and this particular destination. Your ICMP will always have 10.1.1 as the source IP, and the destination IP of the ICMP will always be 20.1.1.1. But your ARP will keep on changing through every interface. Okay. Now here, see, your request ARP has to go. The ICMP has failed because it was not knowing this network. It was not knowing the destination MAC of gig 0/1. Okay, so D, this particular D was not known by the ICMP. So let's see what ARP is trying to do. If I go there, you will see your ARP is trying to say that, hey, I am from C. Okay, my source MAC address is C, and the destination is all Fs. So source is C, which is right here. Okay, and the destination is all F because it's flooding all the ports with F now, and is trying to find out what is the MAC address of 1.1.2/24. This MAC is trying to find out. Now, why it is trying to find that out? Because we already have given that command of the static route in both the routers. That is the path. If you want to go to 20 network, you have to go to the next hop, which is 1.1.1.2, right? So that is your request ARP. Now let's see. The reply ARP will be coming. ARP is going there, and your response ARP will be coming back. So let's check that packet. That is the response. And this is the response ARP. Now you will see in the inbound, which is coming up right here, your source MAC is showing up there now. Okay, your source MAC is D. So this guy has given the info that source MAC is D. Okay, please make a note of that. I'm the guy. And ARP is going to go ahead and flag and make sure that ARP table in the C interface is updated. I hope you're getting the point. The point is that every interface, the ARP will make sure it knows the next hop MAC address, and it will make sure the ARP table is updated, and it will pass that info back to the ICMP, and ICMP, the request process will start again. Again, you will see once the ARP request has came back, you will see your ICMP will start off again. But the ICMP, you will see, it has not started from this point. It is starting again from point A. Because I told you that ICMP in layer 3, your source IP and the destination IP will remain throughout same in the packet flow. Okay, it's only the layer 2 info will keep on changing again and again, right? So ICMP has started and it's going again as a request. It will pass through this and it is going straight to this particular D interface. And again, it fails. Why? Because it is not knowing the next particular MAC address. So it is not knowing the MAC address of 20.1.1. Now, this point of time, we can actually check what is the TTL in the ICMP because it has crossed. Okay, let's see. Let me, sorry, this is our packet. If I open the the ICMP, you will see that the TTL is 127. That is inbound actually. So it has hit the network 1.1.2, right? So it has passed the router, which is R1. That's why the TTL has came down from 128 to 127. Okay, and the outbound is 126 because it has passed the interface from gig 01 to gig 00. This still gig 01, it is 127. The moment it does the hop or the jump here to gig 00 to the exit route, definitely the TTL value will decrease by 1. So by every hop, your TTL will get -1, 128, then -1, then -1 again. If you check the first ICMPs, let's say that this one which got failed, you will see the TTL value would have been there 128, right? But as and when the ICMP is crossing the networks, then the TTL value is getting diminished by 1. So now again, your ARP starts. This is your request ARP. And again, you will see it will start a broadcast. It is starting from E. It tells that my source MAC is E. So this is the source MAC, which is interface gig 0/0. Source MAC is E, and my destination is all Fs. My source IP is 20.1.1254, which is the default gateway, because ARP, like I said, the layer 2 header will keep on changing the source and the destination addresses. So source IP at this point will be this guy, which is 20.1.254, and your destination IP is 20.1.1. So we are very close now. We are going to close it very soon. Now the ARP request has been sent out, and it is going to 20.1.1, and this guy will accept it, and he will say it's me, and it will update the ARP table, and immediately it will send back the ARP response. In the response ARP, going back, and that's how the MAC table in the switch will be updated with 20.1 and F MAC address, and it will go back to the router. It's going back, right? So let's check out the final ARP, how it is. It will be saying that I'm coming from coming from F and going to E. So basically this is the F1, the 20.1.1. Let me just show you the diagram here. This is the F1, all Fs, okay? The F2 is going to E. E is here, right here, okay? And your source IP is 20.1, which is this guy, and destination IP is 20.1.1.254, which is this guy, okay? So ARP only travels from network to network. Just remember that. Straight away, ICMP again starts from here, okay? So once the ARP tables are updated, again, the mechanism will trigger that, okay, ICMP, start off again. Now the ICMP request will pass through all of them. It goes straight to the switch, from the switch goes to the router 1, from router 1 to router 2, comes back to the switch 2, and goes to the 20.1. It's accepted, and ICMP response will be coming back, and it's going back to the router 1, going back to switch, and finally going back to 10.1. This is where the ping will get complete, and if you go back to your ping, you will see reply has came back. First 2 times the request got timed out. That's why sometimes we see that in packet tracer or in any other kind of network as well, maybe the first statement, the first time you get a switch unboxed or first time you get a router connected, your first 1 or 2 ping commands will be timed out, because all this while it was going through all this circle of ICMP and ARP and making sure the ARP tables are updated in all the devices, the laptops and the routers, and of course every interface in the router and the MAC table in the switch. And that's why like 1 or 2 timeout will be happening. And once the tables are completely updated and the ICMP response has came back to the source, it will show you that there is a reply coming up. Okay, and watch at that. I mean, just look, the TTL has gone to 126. It started from 128 because there are 2 hops there. 128 minus 2 is 126. Okay, so that is the packet flow of static routing, right? Fantastic. So this is a kind of a very important simulation. Just go through it like multiple times if you want to, or try it out at your own end. It will really clear the concept that how the ICMP and the ARP works when you are talking about a very basic kind of routing topology. Okay, our next topic is simple one, so I will not take much time on that. A critical one though, that is called loopback. So let me go ahead and just open up my toolbar. Okay, now to understand loopback and what exactly a loopback does, let me pull out, we can just do with 2 routers, that's it, and we can have a connection between them. Okay, we are done. So loopback is something which is a logical interface. See, what happens is currently we have not attached any switch or any laptops or anything here, right? There is no LAN which is connected to the router. Now, there will be instances where you probably will be connecting only the routers at the enterprise level, probably, and then you will check if the LAN will be working or not. And how will you check that? Without connecting the LAN, you can create a loopback interface for the LAN without actually connecting the switch. You can say that, okay, the loopback will be 10.1 or 20.1, like whatever, and that logical interface will be there. And if you can ping that from your original router, gig 0/0 or 0/1, that means that your interfaces are working or your link is up and running. Okay, now let me go and show it to you. If I go to config, CLI, start off. Okay, Now, creation of the loopback is very simple. Okay, first of all, I will just change the host name, and it is interface. Okay, put a question mark, and you see a loopback there. Yes, the loopback is right there. So loopback is a logical interface. It's not a physical one. It is not a real one. You're creating a logical. However, with that you can do the ping, you can do all the stuff and can check without a LAN if the LAN will be working, and also used for troubleshooting purpose as well, and also to make sure that in the initial stage when you are checking your router, that if the loopbacks can be pinged. Okay, so interface, then you say loopback. Okay, and question mark, it is asking for an interface number. Just give 1 and we are done. Okay, press enter, change state to up. Now that means that you do not have to give a no shutdown command there. The loopback is automatically up. Okay, now if I want to give, let's say that if I want to give the loopback on this side as well, let's see, or I can just go and, okay, let me just show it to you. I will say do show IP interface brief, right? Press enter, and you will see the loopback one is showing up here, unassigned, but it's showing up here. Right now, what if I want to go to the interface loopback one itself? So interface loopback one, I can go there, right? I can type in IP address. Okay, I can give something like, let's say 11.1.1.1, and I will say 255.255.255.0, press enter. I don't have to give a no shut command. Okay, no shut is not required in the loopback. Press exit, and let's see, do show IP interface brief, and you will see the loopback is showing with the proper IP assigned, and it is up. Okay, and you will see that the remaining interfaces are down. They do not even have an IP, but the loopback is up and running, which is cool, right? Similarly, I can go to my second one, CLI, and I can say no here, enable config T, host name R2, and I can say interface loopback, let's say 2. Okay, it's changed, and I can say IP address 21.1.1.1. I will say 255.255.255.0. Enter, no shutdown needed. Exit. I'll say do show IP interface brief, and you will see 21 is showing up right there. Loop back to, and it is showing up. Okay. So if I check, look into the interface now I have to make this 2 up and running. Okay. The loopback can be just written down somewhere here with a label, loopback 1 and loopback 2. The other thing is that if I want to show the connected links, will that show? Let's see. Do show IP route connected. So your 21 is showing directly connected. Loopback 2, right? Similarly, if I go to the router 1, I can say do show IP route connected, and that's showing up there as well. Right. So you can use it like a normal connected or a directly connected network and do the troubleshooting, do the ping, do all kinds of like commands there, thinking like it's a logical interface. Okay, so that's all about the loopback. And what you can try out is that once you connect this kind of like networks, you can keep like 4 or 5 loopbacks on each side and make these links up, the gig 0 and the gig 1s, and then try to check how the ping happens and how the connectivity happens from this end, and try to connect a PC here and check how it works. It will all work fine if the connectivities and the default gateways are given proper. But just what I wanted to say is that loopbacks are mainly used for the logical interface or the logical network itself. You do not have to connect the LAN to the router. Without connecting the LAN to the router or the components to the router, just having the routers turned up, you can check the connectivities and test out the connectivities. Okay. All right. So with that, we came to the end of our lab session 2 of routing. Let's meet up in lab session 3. Thanks for watching the video. Have a good time. Cheers. All right. So by now, I'm sure that you would have got some understanding about routing fundamentals. Just rehashing our knowledge on the routing. So routing is what? It's forwarding of packets from one network to another network, right? And apart from that, it's also switching packets from the inbound to the outbound interface based on the routing table, which is stored in the routers. Now, inbound to outbound means, let's say that you have got a router R1, right? And the interface which is connected to the LAN, like the switch or the computers, that's called the inbound. And the outbound is the one which is pointing outside the default gateway, so basically connected to one more router or the internet and so on. So from inbound, the switching of the packet will be happening on the outbound. And which outbound it will happen, like if there are multiple interfaces, R1, R2, R3, and you have got like G0/0, G0/1, G0/2, and so on in each of the routers, then based on that, from the inbound, like from the LAN, it will pick up the correct outbound and go to the next hop, and that's what it based on the routing table. So that's what is about routing. Now when it comes to routing, we have got three kinds of routing. One is static, second is default, and third is dynamic. Static means that, and we have seen that right in the first lab. So static is used when your destination is known. If you want to reach from 10 to 20 network and you know that your next hop is there, then you are just going to add that next hop and you're going to reach the destination. That is called static routing. Now, normally we use the static routing in the case of the hub router. In the upcoming lab, I'll be showing you what exactly is a hub router and what exactly is a spoke router. But right now, just know that hub routers are the ones where your destination or your next hop is absolutely known. All right. Now, your next hop will change based on the destination, which means that if you have got a router, you can either reach like say 20 network on the left hand side or 30 on the right hand side. Uh, each of the time, your next hop will keep on changing. Okay, so your destination is known, but your next hop will change based on the destination that you are going to have for that particular route. Okay. Let me just pick up an annotation here. Okay, and your AD is 1. Now that actually means that your administrative distance for static routing is 1, which we have seen in the earlier labs as well. AD means that now each of the routing or the ways of the routing or the protocols, they will be having multiple ADs there, some default ADs assigned to them. Now if you have got two routers or multiple like routers with multiple paths in them, and each of the path is having a different routing protocol, which we normally use in the dynamic routing, then the best path or the best route path will be selected based on the AD. So static means the AD is by default 1. Okay, and this is what the command that we have seen for the static routing as well, like your IP route, your destination network, your destination subnet mask, and followed by your next hop IP, which is your next hop which you should jump to reach the next network or the network 2. Correct? Now, default routing. So what is that? So default routing is used when your destination is unknown. Now, static we have seen, your destination is known. Imagine that you have got a router, let's say R1, which is connected to the internet. One end is connected to the internet and one end is connected to your local LAN, like your switch and the computers. Now, internet will be having multiple servers, right? Your Facebook and Twitter and Instagram and so on. Now, will you know the IP address of all the servers? No, right? You're going to get connected to ISP and you will be probably knowing only the ISP next hop. And from the ISP, it will route you to the proper server addresses. Now, the default routing is there when your destination is unknown. Okay, you do not know the IP address of the servers which you are going to reach out. Now that's done only on the edge or the spoke router. So there are two kinds of routers we are talking about. One is called the hub router and one is called the spoke or the edge router. Edge means that where one end is connected to the internet or the ISP, and hub is that where one end is connected to the edge router. So hub will be a router which can be placed between two edge routers, okay, and where each of the edge will be having an interface connected to the hub, uh, and edge will be the one where one end of the router will be connected to unknown destination. Okay, we also call that WAN interface. Now in the upcoming lab, I will show you like what do we mean by a hub and spoke kind of router. Here your next hop will not change because like I said, your destination is unknown. In the static, your next hop will keep on changing. If you want to go to 20, you have to use a separate next hop IP. If you use a 10, or if you want to go to 30, you have to use a separate next hop IP. But in the case of default routing, your next hop will always remain the same. You want to go to Facebook or Twitter or Instagram or anything on the internet, you have to go through your ISP router itself. And the ISP router will be always your next hop as a constant. Here also your administrative distance is equals to 1. And the command for the default routing is IP route any destination network, any destination source, subnet mask, and your default next hop. Here this any will be standing for 0.0.0.0. Any destination subnet mask will be 0.0.0.0 again. And of course, your default next hop to reach out to the unknown. Okay. And finally, your dynamic routing. Now, that is one substantial part which we are going to deal with in a deeper dive in the upcoming lessons. But dynamic routing, as of now, know that it's more sophisticated. It's based on algorithms, and it is kind of used in a way where automatically your routing tables will be updated. You don't have to do anything manually there. Once you turn on the dynamic routing, then it will work on the protocol based. So your dynamic routing will be based on multiple protocols, let's say RIP, or we have got EIGRP, or we have got OSPF. RIP stands for Routing Information Protocol. That's got a version 1 and version 2, and the AD is 120. EIGRP is a Cisco proprietary protocol, and that is AD equals to 96, and that stands for Enhanced Interior Gateway Routing Protocol. And OSPF stands for Open Shortest Path First, where the AD stands for 110. Now for your CCNA 200/301 syllabus, RIP and EIGRP are excluded. You only have got OSPF. Okay, and for OSPF, we are going to do a broad, lesson, a deeper lesson with, a couple of labs to show you how exactly it works. Now, one more thing which I want to talk about here is that the static and the default routing. Now we know that the static and the default routing, if you want to make it work, the command says default next hop or next hop IP, right? You need to have either the next hop IP, that's one way. And the second way is that it's based on self exit interface. Now, when I come to the lab, I will show you what exactly we mean by a self-exit interface. But static and the default routing can be either done with the help of next hop IP or with the help of self-exit interface. Static routing, your AD is 1 when you're doing a next hop IP. However, the interesting point is that when you are doing self-exit interface, the static routing AD turns to 0. Now, which one do you think? Like if there are multiple route paths, which will be the best route? Will it be your self-exit or your next hop IP? Of course, your self-exit interface will take the preference because like I said, the lower the AD number, the more preferred it is for the best route. We'll come to all of this slowly, okay, in the upcoming lab. That's all about your routing types. And next we are going to jump into the lab. Welcome to routing lab 3. In this lab, we are going to cover the remaining concepts of static routing, a few of which we have seen in the previous slide. And this will be one of the last labs on static routing. In future, we are going to dive into dynamic routing and get into some labs for OSPF. All right, let's dive into the remaining concepts for static routing. Let me just pull ahead a few routers here. Let's say 1, 2, and let me also get a cloud there, or let's say your internet. Uh, Connect them quickly. Router 0 to 1 and 1 to cloud, right? So let me just rename this router 1. Let's say ISP, and let's say this IP is 1.1.1.1. Okay. Now, if you look into this topology, the router on the far left-hand side, this particular router, what we call the edge router or the spoke router. Now, this particular router will be at the edge of your company, and that will be connected to the internet or to the cloud with the help of your ISP, right? Now, let's say that this is the internet, and there you're going to have multiple servers, right, of Facebook, Instagram, Twitter, and so on, and you will not be knowing the IP address of each of them. So what you do is that from here you can enable the default routing, which syntax says that IP route any destination which is 0.0.0.0, any subnet mask which is again 0.0.0.0, and your next hop IP. And your next hop IP will be this guy, the ISP, which is 1.1.1.1, right? So basically it says that the default routing is to be used when your destination is not known, number one, and number two is that when your next hop IP is always constant. Fine. So that is the concept of the default routing, and this will be your edge router or the spoke router. And this interface gig0/0 is called the WAN interface. Okay. Now let me quickly take you through the example for static routing. So static routing, let's say I get 3 routers here, and let me connect them quickly. Basically the concept of your hub and spoke. So this we connect and this we connect as well. And let me also give some, let's say this router is in network 20, this is in network 10, and this is in network 30, right? Now once we do that, then you will see that this particular router is called the edge because they are connected. I mean, their exit interface will be connected to some unknown destination. However, the router which sits between these two edge routers is called the hub router, because both the interfaces of the hub router gig00 and gig01, on both of them we know the next hop IP. So if I want to get into 20, I know the next hop IP, this guy, which may be 1.1.1.1, and if I want to go into network 30, I know the next hop IP, which is this guy, which may be 1.1.1.2. Correct? So your hub router is best suited for the static routing, and that will be used when your destination host is known, number one, and your next hop IP will keep on changing as per the destination host. Okay, that's all about a quick rehash on the default and the static routing. All right, now let's go to a fresh topology and start working on few of the remaining concepts of static routing. Okay, let me quickly go there and remove this drawing. Okay, so for this, I'm going to pull up, let's say, a couple of laptops here. 1, 2, I will take this side, and 2 more I will take this side. I will take a switch on each side, 1 each, and I will also take routers. That will be again 1 on each of the side. Let's connect them quickly. Okay, and from laptop to switch to laptop, and switch to router. Again, laptop to switch, switch to laptop, switch to router. Okay, and finally your router to router. Okay, that's how the connection looks like. Now let me give some names here or some IP address quickly. The first one we can give 10.1.1.1, and this will be let's say 10.1.1.2. This will be let's say 20.1.1.1, and this will be 20.1.1.2. Right now, here the default gateway gig00, that particular IP address will be 10.1.1.254, and this side it will be 20.1.1.254. Gig01, let me put it 1.1.1.1, and gig0/1 on the router 2 side will be 1.1.1.2. Now let me quickly load the routers. For that I will use the notepad, which is pretty simple, and I have shown that in one of the past labs. We will type in enable config t, and then we will say host r1. If I want to configure, I will say interface gig0/0, and I will say IP address 0/0. The IP address is 10.1.1.254, 255.255.255.0. I'll say no shut. And similarly, interface gig0/1, and here the IP address will be 1.1.1.1, 255.255.255.0. Again, no shut. And finally, we will say do WR, just to write it to the memory. Okay. Now this is my configuration for router R1. Let me quickly go there and just load the configuration there. Paste it, and we are done. Now for router R2, I'm going to just change this. I will make it 2 gig0/0 should be 20.11254. 0/1 will be 1.1.1.2, right? And both are no shut. Okay, let me just go ahead and put this in router 2. Okay, both are configured now. The links are up and running. Now in the laptop end also, I will be just giving the configuration for the laptop. Let's say 10.1.1.1. I will keep it /24. So basically 255.255.255.0, and I will make it 10.1.1.254. Okay. Similarly, for the 20th laptop, I will be doing 20.1.1.1, and here /24 again, 255.255.0, and gateway will be 20.1.1.254. Done. Now I'm going to enable the static routing now, which basically means that I will go to this router and I will say that command is IP route. Okay, and I will give the destination network. So sitting at R1, my destination will be 20 this side, right? So I will say 20.1.1.0, and I have to put the subnet mask, which is 255.255.255.0, and I will put the next hop IP, which is basically your 1.1.1.2, 1.1.1.2. Now that is called next hop IP process. Press enter, it works. I will also show you the way to configure through the exit or the self exit interface. How do I do that? If after the subnet mask, if I press question, you will see I get an option to type in the next hop IP, of course, and I also get the option to do the other way around, like the gig bit also can be typed in there. So my self exit interface for R1 will be this guy, gig 0/1, right? So I will say gig 0/1 and press enter. That too works. Similarly, I can go to my R2 and I will give the same commands. So I will say IP route, and here from R2 I have to go to 10, and I will say 255.255.255.0. My next stop will be 1.1.1.1, right? Enter. I can do this, or I can also do gig. For R2 it is gig 0/1, so gig 0/1, enter. That too works. Now I will give one command, and then after that we are going to check if the ping works, or the connectivity works between the laptop 10 to laptop 20. So if I go to R0, or basically the R1, there I will go to each of the interface Z0/0, and I will say no IP proxy ARP. This command is given to ensure that I take away the proxy ARP from the interface. Okay. Now, proxy ARP is a concept which you are going to take a deep dive and learn it in the CCNP level, not right now, but I'm just going to show you that what happens if I take off the proxy ARP, and then can you do the connectivity, and why not. Okay. So, and most of the commands in the routing or in the switching as well, if you just place a no in front of the actual command, it means that negate that. So no IP proxy ARP, press enter, and then G0/1 you put, no IP proxy ARP, enter. Done, right? Same thing you're going to do in R2 itself. You will say interface G0/0, no IP proxy ARP, and you change it to 1, no IP proxy ARP. Done. Now come to this laptop and check, can I ping from 10.1 to 20.1? Ping 10, ping 20.1.1.1. Will it work? Let's see. Will basically not work out, but in the actual case, without negating the proxy ARP, would have definitely worked out, right? Like what we have seen in the static route labs. The moment you give the IP route command for the static routing, it definitely works out. But here you will see that we gave the static routing commands, but after that, once we negate the proxy ARP, then it's not working. So it means that if I enable the proxy ARP, it works again. Now, what is proxy ARP doing here? Okay. So let me just get into the simulation mode and take off all the filters. Just go for ARP and ICMP and check it out what's going on. So I will go to this 10.1, type in ping 20.1.1.1, enter. Once I press enter, you will see ARP or the ICMP is coming there. ICMP will be flowing through the first one. Now it's a little bit of error here because we already have done the first ping, and in packet tracer you have to start it fresh if you want to see the actual packet flow. But that's fine. I'm going to share with you where exactly it gets stuck at the ARP stage. So once it returns and once it starts with the first ARP, you will basically see where it gets stuck. ARP is there, right? ARP is coming. So ICMP will not be able to take the first one because it will not know that what's the MAC address or what is the destination IP, and how that mapping is done with the map address. So your ARP will help you to find out the MAC address based on the destination IP, right? Now ARP is trying to find it out from the interface here. Now this interface, so ICMP has failed here, right? And then ARP will move. Now ARP moves mean that, let me just type in what is the ARP nomenclature here. Your source IP will be 1.1.1.1, and your source MAC address, let's say it is C. Okay, just getting a number. Your destination IP address, that is your 20.1.1.1, because remember your routes are connected now. your 20 is connected to this particular router or the gig 01, which basically means that your 20 can be reached with the help of 1.1.1.1. So that's why your 20 is the destination IP address, and your MAC you don't know there, and you say FFFF, right? Basically it will hit here. Now once it goes there, this particular gig 0/1, it will see, okay, fine, 1.1.1.1 is coming to me, fine. But 20.1.1.1 with the flooding of the MAC address in the broadcast, I cannot take it because I am not 20.1.1.1. I am 1.1.1.2, and it will drop that ARP. Okay, let me just take you further. You will uh, see the ARP packet will go there and it drops there. So your ARP do not have any role to play here. The ARP will actually get dropped, and your communication will fail. So what is helping you to work here in this kind of concept is that proxy ARP. Remember one thing, that your router is the device which is going to stop all broadcast by default. So your router, this port, if you flood it with MAC address F, it's not going to flood it outside immediately because your router will stop all the broadcast by default, right? And also your this particular port or the router knows that's okay, this is coming to me, but 20.1.1, that's not me. Okay, I am 1.1.1.2. It will drop it, and the ARP drops. If the ARP drops, and you know that very well, that if ARP drops, then your destination MAC address cannot be found with the help of the destination IP address, and your ping or the connectivity will completely fail. So ICMP will not work out because ICMP depends on ARP to actually work out. So that is the entire flow which I wanted to show you here. Now let me go back to real time, and I will just go to the routers and enable the proxy ARP. Again, I said the proxy ARP, the concept is not a part of CCNA. Don't worry on that. Just wanted to show you this. Once you get into CCNP, definitely proxy ARP will take close to 30 minutes to get the points straight. And there's a very nice article in Cisco site which talks about proxy ARP, official article. It's very easy to read and to get the points straight. Okay. So let me go ahead and enable the proxy ARP. And proxy ARP has to be enabled on the interfaces. Okay, 0, and I will say IP proxy ARP. Okay, again I will say 0/1 IP proxy ARP. Done. Similarly in router 2 also I will do that, and I will say 0/0 IP proxy ARP, 0/1 IP proxy ARP. Okay, now let's see if from this laptop I can ping 20.1. Okay. So packet tracer, it's an error actually because we have tried the ping the first time, but in reality your ping will fail 3 times, because if you look into the diagram here, your first ICMP will fail right here at this point, and second will be failing right here at this point, and third it will cross this again, it will fail somewhere here at this point. So 3 times the ICMP will fail, and then finally when it grabs the destination MAC address based on which the flow happens, that's when the ping will be coming back. So that's why you see that this last one is showing up, which is proper. The first one is not the proper one because, like I said, it's an error from the packet tracer. It should actually time out 3 times in the first instance. Okay. So if I do the ping once again, now you will see it absolutely works all the 4 times. So your proxy ARP is one of the concepts which you are going to learn in your CCNP. I just gave a little bit of high level view. What happens if you disable the proxy ARP? Now let's see one more thing. Can you check in a router that, can you check out if proxy ARP is enabled or not? See, by default, the routers will be having the proxy ARP enabled. Okay, so let me check it out. Do show IP interface G0/0, and you will see your proxy ARP is enabled, showing up right here, right? So that's how you find it out if your proxy ARP is enabled on the router. So that's about the concept here. One more quick thing which I wanted to just set through before I end this lab. So this one, this router 1 and 2, let's say if they were connected with a serial interface. Okay, we don't use that any longer, like your T1 connection or your T2 connection and all that. Now, serial interface, when I talk about, probably I can explain that by taking a text here. Okay, let's say you're talking about serial interface. Okay, and your both ends will be like S0/0 and S0/1 and so on, right? Now there is no MAC address, okay, no MAC address on serial interface, which means that both the things work absolutely fine. What is that? One is your next hop IP and one is your self exit interface. Both the stuff works fine. Okay, and serial is not used these days, and also in the exam you will not find that, but I'm just trying to say that, yeah, in the serial both the options for static routing work absolutely fine, your next hop IP and also your self exit interface. The reason is that we do not have any MAC address on the serial interface at all. Okay, so there is no concept of that you have to go ahead and enable the proxy ARP or something, because it's not having any MAC address. Now when it comes to Ethernet uh, interface, okay, here we definitely have got the MAC address, and the only one which works out is the next hop IP. Okay, if you want to make this self exit interface work out, then you have to make sure that your proxy ARP is enabled. Again, in CCNP you will actually learn that when do we use the next IP hop and when do we use the self exit interface, because they are not to be used everywhere. There are certain places where you use the next hop IP and there are certain places where you use the self exit interface. So again, that's a concept which we are keeping for the CCNP level. That's not a part of the CCNP or the CCNA scope. All right. With that, we came to the end of our lab on the remaining concepts of static routing. Meet you again in dynamic routing. Thank you for watching. Cheers. Dynamic routing. Now that we have seen the static routing, we have seen that it's kind of manual, right? You have to type in your destination network and your next hop IP and so on, and then only you can reach a particular destination. Uh, Dynamic routing is much more sophisticated, and it's the most popular way of routing. So the plus points of dynamic routing will be that uh, your updates for the routing will be automatic. As and when your topology will change, you do not have to manually get inside and you have to update the information. That's kind of uniformly spread across within the router group. And you no need to configure the destination networks manually like what we do in static routing. So it's a lot of ease and the configuration is easier, and more than that, managing that for a large and complex kind of network with a lot of routers there, you can do it with a lot of easiness compared to static routing. Now when we talk about dynamic routing, we have got three kinds here. One is the distance vector, one is the advanced distance vector, and one is link state. So distance vector is actually RIP, or what we call the routing information protocol. That's a pretty old method, and the metric is least hop count. Okay, we'll just come to that slowly, that what do we mean by the metric. The advanced distance vector is EIGRP. Now that stands for Enhanced Interior Gateway Routing Protocol, which is a proprietary protocol by Cisco. And here the metric is least feasible distance, or FD. And finally, the link state for OSPF, which is open shortest path first, that metric is least cost. And the formula for cost is 100 divided by bandwidth. So in the current CCNA syllabus, you do not have either RIP or EIGRP. The only protocol or the method that we have got in the CCNA syllabus is OSPF. So we'll focus on OSPF only, but in the first two slides, I'm just going to explain to you or give you a high level view of OSPF in comparison with the other routing protocols, and then we will dive straight away into OSPF. Now, if you look into this diagram here, okay, right, and let's say that we have got R1, R2, and R3, three routers. Now from R1, let's say X network, you would like to reach R3, which is Y network, okay. Now we have got two links here. One is the Airtel link, say ISP, and 10 Mbps link, and one is the Tata link, again one more ISP that's having 20 Mbps link. Now, if I look into RIP, okay, RIP will choose the path, not the Airtel, not the Tata, but the Airtel, because it depends on least hop count. Though in a very initial scope, you see that the speed here is higher, 20 Mbps, but still RIP will pick up this link R1 to R3 through Airtel because its metric is based on least hop count. So whenever that protocol will see that, okay, this is the least hop count, and hop means you jump on a router. So number of hops means number of routers. So to reach from R1 to R3, it's just one router only. And that's why it will say least hop count, I will pick up the Airtel link. When it comes to EIGRP, there the metric is least FD. Now FD has got a very complicated formula. I'm not going to share that here because like I said, EIGRP and RIP, they both are not in scope of your CCNA syllabus, but just to have a high level view. Now FD means it's basically the opposite of bandwidth. So more the bandwidth, your FD will become lower, and EIGRP will prefer a lower FD. Okay, now if you look into this, more bandwidth is here, so EIGRP will pick up Tata 20 Mbps because it says more the bandwidth, least is the FD, and least FD is what is the metric for EIGRP. OSPF, that method of the routing is called link state. Now cost, like I said, cost is 100 by bandwidth. So for Airtel the cost is 100 by 10, which is 10, and for Tata it is 100 by 20, which is 5. So definitely least cost. This R1 and R2 is the least cost, so that's why OSPF will choose this path to reach R3. Okay, as simple as that. Now let's come down to the protocols. Like I said, RIP is there, EIGRP is there, and OSPF is there. So RIP, the administrative distance is 120, and we have got a concept here. That concept is called multicasting. RIP's multicasting address will be 224.009. Now 224.009, that is a class D address, and multicasting actually means that you relate to a group of devices. So in the network, we have got three kinds of communication going on. One is the unicast, like 1:1. Then one we have got the broadcast, which is 1 to all, and multicast is 1 to many, not all. Okay, just a group. It's something like a channel, a TV channel, where if you have subscribed to that, then only you can get to have a look into the information. If you're not subscribed to that channel, then you do not get to see that information. That is multicasting. So RIP says that if it wants to communicate with a group of other RIP enabled routers, then the multicasting group information is 224.009, right? And the administrative distance for RIP is 120. EIGRP, the AD stands 90 or 170, and here also the multicasting address is 224.0010. And when it comes to OSPF, the AD is 110, and here we have got two multicast address which we are going to check why they are in the OSPF lessons, and we have got two of them, 224.005 and .006. Okay, so that's about the three different routing protocols. And finally, the routing is also based on the algorithms. So algorithms is like your mathematics on the background, okay, the coding, okay, that will enable to make sure that, okay, if this is the algorithm, then based on this the routing protocol will calculate the metric. Now the algorithm for RIP is based on Bellman-Ford. Okay, the algorithm for EIGRP is dual. Okay, and the algorithm for OSPF is SPF, shortest path first. Like I said, we are going to focus only on the OSPF after some time, so I'm not really going to double click on the items of EIGRP and RIP, but ensure that yes, these are the algorithms, and OSPF works on SPF, and OSPF has got the AD110, we have got the multicasting address 2245 and 6, and it's a linked state protocol, and cost is the metric, and the formula for cost is 100 by bandwidth. Right. Two more things here to be discussed. Number one is the types of protocols. Number one is classful, and number two is classless. Now, classful is pretty old one, RIP version 1. Okay, the initial version of RIP, that was classful. Classful means that something which do not support subnetting, which means that let's say you have got a router R1 and R2, and on the R1 you are going to transfer the data and or the packet and the network information and the subnet mask. Uh, if you have customized the subnet mask, like if the class or the IP starts with 10, we know that it's a class A, and the subnet mask will be /8, right? However, if you have customized that and you have changed that /8 to /24, what's going to happen is that in a class full, when this particular packet will reach on R2, okay, it will convert that, it will take away that custom subnet mask and again make it back to /8. It will not carry the custom subnet mask. Subnetting information is not carried over in classful routing protocol. However, the beauty of classless is that it will support the subnetting as well, or the custom subnetting as well. And all of them, RIP version 2, EIGRP, OSPF, they all support classless subnetting or classless protocol, which means that in this side, if I say 10.1.10/24, and if I transfer the packet to R2, not only the network information is transferred, however, along with that, the subnetting information is also transferred. So /24 will remain as /24 on the other end. That's the beauty. Okay. The second concept is about load balancing. Now, load balancing is of two types. One is called the equal cost load balancing, and one is unequal cost load balancing. Equal cost load balancing is supported by all the protocols, okay? And unequal cost is supported only by EIGRP. The equal cost means, let's say I've got a router R1 and a router R2, and they have got two links there. Okay, now each of these links are having the similar bandwidth, like 20 Mbps, which means the cost will be 100 by 20, which is 5. So cost is 5 here and cost is 5 here as well. Now from here, from R1 to R2, if I am planning to send, let's say, 4 packets, okay, they will be distributed evenly, like 2 on the top link and 2 on the bottom, and they will straight go to R2. However, let's say I change the bandwidth, I change this 20 to 100, which means then my cost will be 100, sorry, 20 to 10. So my cost will be 100 by 10, which is 10 here, and this is 5, right? Now, if this is 10 and this is 5, then what's going to happen? All the protocols or all the packets which are coming here, they will actually go through the least cost, which is 5, and they will neglect the 10. They will not go through the 10, they will go through the least cost, which is 5, and all the 4 packets will be going through this only. Okay, now that problem is solved in EIGRP. They have got a concept called unequal cost load balancing, how they do that. But like I said, EIGRP is not in your CCNA syllabus, so we are not really going to double click on that and check on that. All right, with that, we cover up the basics of dynamic routing, and then we step into OSPF. Welcome to OSPF lesson. OSPF stands for Open Shortest Path First. Now, in the previous routing lessons, we already have gone through a few of the key features of OSPF. In this presentation, I'm going to share all the key points of OSPF in one single shot so that it's easy to remember, and also we get a consolidated kind of quick glance for OSPF. Now, prior to we do that, just a few key points here. Number one is uh, in the CCNA syllabus of 200-301, we do not have the routing protocols as RIP version 1 and 2 or EIGRP. It is only OSPF, which is in scope of the exam. Now, OSPF is divided into two parts. The basic foundational stuff is in scope of the CCNA exam, and the deeper dive is happening in CCNP level. So in this particular OSPF lesson and followed by the two labs, we are going to go through the components or the features which are only in scope of the CCNA level of exam. For CCNP, we are going to cover that in the CCNP training. All right, so let's start off. Let me quickly grab annotation here. And okay, first thing first, the administrative distance of OSPF is 110. OSPF is a link state method of routing. We also have got the distance vector routing method, and we have seen that RIP is a part of that. OSPF works on SPF algorithm. SPF stands for shortest path first. Now, what SPF does is once your routers are turned on with OSPF, then SPF will do the calculation for the metric, which is cost. So the metric for OSPF is cost, and the formula for cost is 100 divided by bandwidth. The least cost value is the best here, which means the least cost value is the best route in OSPF. It will always go for the least cost value link. OSPF supports unlimited hop count. If you look into RIP, it will support like 15 hop counts. Now, hop count means the number of routers which you need to cross to reach your destination. In EIGRP, the maximum number of hop counts that we support is 255. But OSPF has got no limitation as such. It supports unlimited hop count. It supports classless protocol, which means not only the information of the network, but along with that, the subnet mask information is passed as it is from router A to router B, which is awesome because if you're going to customize your subnet mask, okay, let's say for a 10 IP, you push it to /24, OSPF will keep it exactly like that. It is not going to change it to, let's say, /8 because the IP starts with 10. OSPF routers, they always share their updates based on the multicasting groups, and the multicasting IP that they use is the class D IP address 224.0.0.5 and 6. So if there is an update for any router and the router group is there, like 10 routers, like they belong to one OSPF group, you do not really have to go to manually each router and share that update. You just have to share that update in the multicasting group, and the routers who are subscribed to that group because they have been turned on with OSPF, they will be getting the notification from the multicasting IPs and they will be automatically updated. OSPF, it supports load balancing, but only for equal cost. For unequal cost load balancing, that is only supported by EIGRP. OSPF is a layer 3 protocol, a network layer, and the protocol number is IP89. Now, when it comes to OSPF, you will see a kind of packets there, and one of them is called the hello packet, which I'm going to share in the next slide itself. Hello packet is the initial packet which is sent out by the OSPF router to say that, hey, I'm here and this is my IP and so on. Okay, that hello packet will be sent every 10 seconds, and the dead will be sent every 40 seconds. We'll come to this in detail. OSPF supports 3 types of authentication. Now, authentication is needed, because let's say you have got 10 routers who belong to a OSPF group. Before you ensure that the updates are shared amongst the routers, you have to make sure that the routers are authenticated to each other. If you do not ensure that, then definitely a security breach will happen. And once the update is shared, maybe it's going to through a security loophole. It's being taken over by a hacker, and all the key information will be passed on to a hacker. So in order to make sure that your environment of the OSPF is secured, you make sure that your routers are authenticated to each other. Now that's being done by three ways: T0, T1, and T2. T0 is the default way, which we call the null authentication way. T1 is the plain text, and T2 is the highest one, which we call MD5 or hash method. Again, we are going to cover in detail about most of the things which we're talking here in the labs. All right, let me quickly go ahead and let's move. Now, the OSPF process, like I said, OSPF has got variety of packets, and it's also got variety of tables. So let me go ahead and again pull in annotation here and quickly share. So the three tables which we talk about the OSPF or talk in the OSPF is number one, NT or the neighbor table. Number two is the DBT or the database table. And number three is the RT or the routing table. So let's see how it works. First thing first, we have got, let's say, R1, R2, and R3, three routers which are connected through links, and we have got the R1, R2, and R3. The R1 and the R2, they are having the loopbacks. This is like 10.1. This is like 20.1. And the interface G0/0 in the R1 is being connected to 1.1.1.1, and here in R2 it is 1.1.1.2, right? Now, first thing first, how the OSPF will happen and how the tables are updated and what are the packets there. So let's see. Let me quickly take this annotation off from here and let's start off. First step is that RID. RID stands for router ID. In OSPF, we have got a concept called router ID. Each router will be having a router ID, and the router ID will be the highest IP address in the router through the interfaces. So in R1, we have got the loopback address, which is 10.1.1.1, and we have got the G0, which is 1.1.1.1. Let's say the R1 to R3, that connectivity is like 1.1.1.3 or something. So our ID is 10.1.1.1, the highest one. Also, remember one point here. Even if your other IP addresses are higher, okay, if it's a loopback, the loopback will supersede the other IPs. Let's say one of your links was like 11, but still your loopback will be the router ID. If it's not a loopback, then OSPF will check the highest IP address. Again, in one of the future labs, we are going to talk about how the election process of the router ID happens. So on the R1, the router ID is 10.1.1.1, and R2, the router ID is 20.1.1.1, which is again the highest IP. That's the loopback address in R2. Now, the first packet that goes through from R1 to R2, let's say, is called the hello packet. Hello is the first packet sent across the moment you turn on the OSPF. And that means that, hey, I'm here and this is my IP address and so on. Now, hello says that the router R1 is sending to R2 1.1.1.1 because hello will be sent through the interface connected between the routers. So through G0/0, the hello will be sent out, which is 1.1.1.1, and it is not going to be sent to 1.1.1.2. Like I said, it's going to be sent out to the multicast group 224.0.0.5 or 6. Now, one more thing, it is also going to send the router ID along with the hello packet. The hello packet will be sending also the interface IP, and apart from that, the router ID as well. Now, once the hello will reach R2, it will say that, okay, fine, I know this, I don't know this guy, 1.1.1.1, and the router ID is 10.1.1.1. Let me store that address in my neighbor table. That neighbor table of router R2 will be storing this address. Something like two friends. The first friend says that, hey, my name is Jim. And the second one says that my name is Tom. So Tom will be remembering the name of Jim, and Jim will be remembering the name of Tom, right? So here R2 will remember the router ID of R1 that is stored in the neighbor table. And once that's being done, R2 will also be sending the hello packet, which is going from 1.1.1.2 again through the G0/0. And again, it's being sent out to the multicast group IP 224.0.0.5 or 6. Once that's done, along with that, it will also send out the router ID in the very similar fashion what R1 did. Hello packet from R2 will be now going to R1, will say, hey, R1, I know that you are 10.1.1.1. I am 20.1.1.1. And immediately R1 will be storing that data in the neighbor table. So that is about your neighbor table and the hello packet. Now, once that's being done, then we will get into the DBT or the database table. Now let's see, prior to that, if you look into the direct routes which are connected, like direct routes will be showing like C, right? C-10 and C-1.1. So R1 is connected directly to 10.1.1.0 and also to 1.1.1.0, right? Similarly, R2, the routing table will be looking something like this. C is 20.1.1.0 and 1.1.1.0. This is the initial stage. Once you trigger the OSPF on the routers, then what's going to happen? The packet will be sent from R1 to R2, and that packet is called DBD or database description. Now, this particular packet will be actually sharing both this info that, hey, R2, I have got 10.1.1.0 and 1.1.1.0 in my routing table. You can have a look into them, and if you want, keep a record of them. So DBT is sent across. Now R2 will be seeing that, okay, 1.1.1.0 is with me, so I will leave that, discard that. I will just store 10.1.1.0, which is not with me. And now you will see the prefix of 10.1.1.0 in R2 is changed to O. C means connected and O means OSPF. So that is the OSPF route which R2 has got from R1. Now, once R2 has received the OSPF route, it will be sharing back something called LS acknowledgement, okay, or link state acknowledgement, which means that, hey, now I've got the 10.1.1.0 from you, and this is showing that, yes, I have received that from you. Thank you. Now, similarly, the table will be shared from R2 to R1. So R2 will say that, hey, R1, I have got 1.1.1.0 and 20.1.1.0 with me. And R1 will say that, 1.1.1.0 is with me. I will discard that, but I will pick up 20.1.1.0. And it picks that up. And that is called the OSPF route, which R1 will pick up from R2. And that's how the database table will be formed between R1 and R2 without you doing anything. You have just turned on the OSPF, and R1 and R2 will automatically exchange their routing tables and will keep a record of it. Pretty cool, right? Now, similarly fashion, you will see that we have got the link state acknowledgement sent out from R1 to R2 saying that, hey, thanks, I received the 20.1.1.0. I'm completely okay here. So that's about the database table. So till now we have seen the hello packet, what it does, and we have seen the neighbor table. The hello packet will ensure that your neighbor table is formed. Secondly, we have seen the database descriptive packet or the DBT packet, which will ensure along with the ls, that your database table is being formed. Okay. And finally is a routing table. Routing table means RT. That means that what is the best route. Now we know that SPF will be working on the routers because OSPF is there. SPF will find out the cost on each of the links, and based on the cost, which is 100 by bandwidth, it will actually find out the best route to reach from R1 to R2. And that route will be plugged into the routing table that's called OSPF 20.1.1.0. Similarly, on the other end, you'll be having OSPF 10.1.1.0. Pretty simple. So we have got three kind of tables here, and we have seen two kinds of packet: hello packet and the DBT packet, and of course the link state as well. Now these are the following show commands which you use to find out your neighbor table details, your database table details, and of course your OSPF routes in the router. So show IP OSPF neighbor, show IP OSPF database, and of course show IP route OSPF. Now there are two other link state packets. One is called link state request and one is link state update, LSR and LSU. Now these are only used when there are changes in the network. So any kind of change like a modification or addition or a deletion of a network from a routing table, those kind of things will be updated with the help of LSRs and LSUs. We'll come to that in detail in the future. So that's all about a high level view of the OSPF process and how it works when the OSPF is turned on the routers. Thanks for watching. And now I will be getting you into the lab. The first lab will be based on the OSPF, the first process where we are going to turn on the OSPF, the basic one, and check out how the OSPF is turned active for the routers and how it works with all the show commands. And then we are going to have a lab 2 where I will take you into detail about various elements of OSPF. Thank you. Welcome to OSPF Lab Part 1. So in this lab, we are going to check out how the OSPF will be configured on the routers and how do we verify the configuration of OSPF based on show commands. So let's dive in. Let me pull up some routers here. I will get 3 of them. And let me just give the names here. This is R1, this is R2, and this is R3. Okay. Let me connect them quickly. R1 to R2, okay, and then R2 to R3, and finally R3 to R1. Okay. Once it is done, let me quickly give some names here. Zoom this out. Okay. Let me give the network names and the IP address. So first thing first is that I will give some loopbacks. So for R1, I will give the loopback. It is 10.1.1.1. R2, I will give the loopback. 20.1.1.1. And R3, I will give the loopback. 30.1.1.1. Okay. Now, between R1, okay, just try to. Fine. Now, let me just give one more the IP address to the interfaces. Between R1 and R2, I will keep it simple. I will make it R12, so it is 12, and since it's R1, 12.1.1.1. Okay. R2, I will give it 12.1.1.2. Okay, I'm just taking the names from both ends. Similarly, R2, R3, I will make it 23. R2, R3 is 23.1.1.2, that is R2 end. And here I will say 23.1.1.3. Okay. Here, this interface will be 13.1.1.1. I'm taking R1, R3, and again R1, R3. I will take 13.1.1.3. The nomenclature is like simple. I've taken the like if it's R1, R2, I've taken 1, 2, which is 12. Then dot 1.1.1 means the R1 end. Okay, so 12.1, 12.2, 23.2, 23.3, 13.3, and 13.1. Cool. Now, first of all, we will go ahead and we are going to load the routers with the configuration of the basic network and the loopbacks. For that, I will use a notepad because that's the simplest way and the fastest way. I will use for the R1, let's get pretty fast. Enable config T, and then I will say host name is R1. So first is interface loopback, that is L1. And I will say IP address, this is 10.1.1.1, 255.255.255.0. We do not need a no shut, it's a loopback interface. The second one is interface G0/0, that is IP address 12.1.1.1 facing R2, 255.255.255.0. Okay, and this is no shut. And interface G0/1, and this will be IP address 13.1.1.1, 255.255.255.0, no shut. Okay, so that is the entire for R1. Let me just go ahead and paste this in the R1 and load it up. So here is R1. Let's go for no, return, and go for paste, and we are done. Okay, R1 is over. Now let's come to R2. I will give it R2 here. Here the interface or the loopback will be 20.1.1.1, G0/0, that is 12.1.1.2, 12.1.1.2. Here it is, and 0/1 is 23.1.1.2. 23.1.1.2. So one is 12 and one is 23, and we have given the loopback. Let's copy this, go to R2, and load this. Okay, R2 is done. Now let's come to R3. Before I do the R3, let me just go ahead and change this. This is R3. This is 30.1.1.1. 0/0. That will be 23.113. And 0/1 will be 13.113. You can double check it. Loopback 30. 0/0 is 23.113, and 0/1 is 13.113. Okay. No shut. This is the one. We'll see. And let's come to R3 now. Okay, R3 is loaded as well. Now I need to check if what are the connected routes for R1, R2, R3. If I go to R1, let me check what are the connected routes there. What is the command? Do show IP route connected, right? And we've got 3 routes, 10, 12, and 13 is directly connected, and there we go, 10, 12, and 13. Similarly for R2, I will check the connected routes. Do show IP route connected 12, 20, and 23. Perfect. And let's go to R3. And we will say to show IP route connected 12, 13, 23, and 30. Perfect. Okay, great. Now we are going to turn on the OSPF on the routers. And how do we do that? Very simple. The command is extremely simple. So let's go to R1. Now the first method to do is that we are going to interface after interface, and in each of them we are going to turn on the OSPF. Okay. And after that, once that's been done, then I'm going to show you one more method where you can do all the things in one shot. So let me go to interface loop back one, right? And then I will say IP OSPF question mark. I have to give a process ID, which is this between 1 to 65,535. Just a number you give, you choose any number. And let me choose a process ID like 100, question mark. Then you have to give an area. Now, OSPF works on the area concept. Now, area 0 in the OSPF is called the backbone area. Now, in OSPF, uh, area 0 is the backbone, and the areas which are not under 0 is the non-backbone area. Now, if you want to configure, if you want to make your OSPF work, you must need a backbone area through which all the routes will communicate. And also, the backbone area is being needed because without that, your non-backbone area will not be able to communicate. Okay, we are going to come into details on that. But right now, for this level, just know that we need to have an area 0 as a backbone area. So I will say area and I will say 0. And let's go for the area 0. That's it. It's been turned on. Similarly, I have to go to the other interfaces as well. We have got gig 00 and 01. So I will say interface gig 0/0 OSPF and 0/1 OSPF. For R1, OSPF is turned on. Okay. Now for R2. R2 again, I will say IP OSPF process ID. Sorry, I have to first go to the interface. Look back one, and I will say ISP OSPF process ID 100 and area 0. Press enter. Okay. Now again go to interface gig 0/0, and this is your OSPF command. And then you go to 0/1, and here goes your OSPF command. Done. You're done for the R2 as well. Now let's go to R3 and turn on the OSPF there. So again, interface, loop back one, IP OSPF, process ID, area 0, we are done. And we will say int gig 00, OSPF turned on, gig 01, OSPF turned on, and we are getting it. Okay. So the OSPF is configured or turned on for all the three routers, right? Now, few more things here. We already have seen the concept of the router ID, which means that each of the router will be having a router ID. Now, router ID by default will be the highest IP amongst the interfaces. But if it's a loop back, that will supersede. So in the case of R1, the router ID will be 10.1, the router R2 it will be 20.1, and R3 it will be 30.1. Okay. Again, in the coming lab, we are going to check the election process of the router ID. So now let's see for R1, if I go and check out the show commands for OSPF. And what are those commands? So first I will say, first we are going to check the neighbor table. So do show IP OSPF neighbor. And you will see the neighbors of this. So for R1, R1 is 10. Your neighbor is R2 and R3, right? And so your neighbor here will be 20.1 and 30.1. Basically, it's going to only represent the neighbor with the help of the router ID. So 20 and 30 is shown here itself. That's your neighbor ID, right? Now, next two columns, the priority and the state, which is full or the BDR, that all will be discussed in the upcoming lab, not in this one. And here is the address. Address means the next hop. So if I want to reach to 20.1, let's say from R1, I want to go to 20.1, then my next hop will be 12.1.1.2. That's the one. And from R1, if I want to reach 30.1, then my next hop will be 13.113. And that is my next hop. So these are the next hop IPs, and these are the router IDs for the neighbors. Perfectly shown. Now I will be checking out the database. So database table can be seen, do show IP OSPF database. Now that is how the databases are shown, and you will be seeing that the process ID, which we mentioned, is 100, under which all the information is coming up. Now for CCNA scope, you really don't have to know the complete meaning of this command. Just remember the command, but in the CCNP level, we are going to take a deep dive into the database options and what is the command showing up here. Okay, I just wanted to show you how it looks like and if it's working or not. And the last command is about when you check the route tables. So you say do show IP route OSPF, right? And these are the OSPF routes here. See 20.1 and 30.1, like 30 network, then 23 network, and 20, and all of these are having OSPFs here. Now, also one more thing I wanted to show you here is that OSPF will be running the SPF, right? And the shortest path first algorithm will be making sure that it finds out the metric cost here, which is 100 by bandwidth, right? Now, how do I find out the cost? So let's say I want to find out the cost for link for G00, let's say, okay, 00, which is 12.1.1.1. How do I find it? I will say do show IP OSPF interface G0/0. Press enter, and you will be seeing the cost is showing up here, which is 1. So based on that, I can find out the cost for all the links, cost for this one, this one, and this one. And all the links will be 1 here actually, because we don't have a separate kind of bandwidth speed for the links. So 111. So if I want to reach from R1 to R2, my best path is this path only. 0/0 and showing the 12.1.1.1. I will not be going through 13 and then jumping this router and coming to 23 and then going for R2, because then my cost will be 1 + 1, which is 2, which I don't want. My cost will be 1 here, the least cost. So that's how we calculate. Okay, that's how OSPF checks what is the best route based on the least cost. There are multiple stuff here which we will be showing most of the stuff in the upcoming lab, like your hello packets here, which is showing up here, and then your router ID, the integration process, your broadcast types, and all the stuff. Okay, most of the stuff will be shared in the upcoming lab, and a lot of the other details that will not be shared in the upcoming lab as well. Those are part of your CCNP scope. Okay. Similarly, I'll be going to the other routers as well, and I will configure the OSPF. So let's go to R2. I mean, it's configured there. I will just quickly have a check if it's working. So exit and say do show IP OSPF neighbor for R2, right? It is 10 and 30. Sitting at R2, 10 and 30 are your neighbors, right? And again, your address. So for 10, the next hop is 12.1, which is right here. And for 30, it should be 23.3, which is right here. Perfectly correct. I can also see the database here. And this is the database command working. And if I want to see the routing table here, so do show IP OSPF route. I think I just typed it incorrectly, IP route OSPF. Okay, so that's the routes which are showing up here. Okay, and if you look into this /2, okay, from 10. So R2 is here, right? And if you want to connect from 10 via 12.1.1.1, 110 by 2. If you go from 13.1.1.0, that is via 12.1, that is again 2 here. So like that, all the hops are being shown here. Okay. And the cost, like I said, you can find out for each of the link, the cost will be directly shown there, right? So for the loopbacks also, you remember that loopbacks will also be having an individual cost. Like loopback cost is 1 and the link cost is 1 as well. So let's say from 10, I want to find out what is the OSPF cost here, 10.1.1 a loopback. So 10, the loopback cost is 1 plus the link cost, which is here to here, like 12.1.1.1, that is also 1. So 1 plus 1 is 2. Okay. Similarly for 13, now 13 is 13.1.1.0 will be here itself. This from this to this, which means your 30 will be calculated. 30 is the loopback, which is 1 plus your 12.1. So this plus this again 1, that is 2 here is showing up. So like that, the cost will be calculated on the OSPF based on the loopbacks, which is 1, and the cost of the link also, which is 1 in this case. Like 30 is shown right here by 2, right? Okay, so let's go to R3 now and check it out if the OSPF is working there. Okay. First is do show IP OSPF neighbor, and you get it from R3. Standing at R3, my neighbor will be 10 and 20, which is your 10 here and 20 here, R1, R2, and it will represent it with the help of the router ID, correct? Address, if I want to reach 10, then my next stop will be 13.1. So from here, if I want to reach 10, my next stop is 13.1. And from here, if I want to reach 20, my next stop will be 23.2, right? 23.2. Shows absolutely fine. And now let me check out if the database command works. That works as well, and the process ID is showing up here as 100, which we chose. And lastly, the routes here. So do show IP route OSPF, and you will see all the routes are showing up here. Okay, so works absolutely fine, and that's the basic foundational way to configure the OSPF. Okay, now before we get to the next step or the next method of configuring the OSPF on the routers, let me just explain one more thing, and then probably from there we can take on. Let me just pick up a text box here. Okay, a concept called wildcard mask. Okay, now wildcard mask is what? Wildcard mask is basically your inversion of the subnet mask. Okay, or we can say that the global broadcast address minus your subnet mask. So let me show you. Let's say /24. What is the subnet mask? We know that 255.255.255.0, right? Now, the wildcard mask will be, the WM will be the opposite of this. If you just minus this from 255.255.255.255, then you will see 0.0.0.255, right? Similarly, let's say /8, the wildcard mask will be, so it is 0.255.255.255.255, right? That's how it is. Okay, so wildcard masks are used widely in your EIGRP, in your OSPF, and of course when you are going to configure your access control list or the ACL, those kind of situations you will use a lot of wildcard mask. So the next method that I'm going to show you on how to turn on the OSPF without going to each of the interfaces, then you should be knowing wildcard mask concept. Okay, so that's about the wildcard mask, and now let's get into our lab here. Okay, so I go to R1, and let me just configure the OSPF in the other way. What I do here is that just take this annotation off. Okay. Now here what I do, I say router. Router is also a command, right? It's a router. Sorry. Yeah, router. And let's see what's going to come up. So question mark, and you will see all the protocols are showing up: BGP, EIGRP, OSPF, and FRIP. So I will say router OSPF, question mark, process ID. Let's choose 200. Then question mark, nothing is there. Enter. Right. Now, once you choose that router OSPF with the process ID, then your next step will be to just share the network with the wildcard mask and the area. So network, and network you're going to choose, let's say 10.1.1.0. We have got three there, right? One is the 10, and one is the 13, and one is the 12 for R1, right? So for 10.1.1.0, I will use, if I press the question mark, it will ask me wildcard bits. It's not going to ask me the subnet mask. So here it is /24, which means I will use 0.0.0.255. That is my wildcard mask. And then it will ask me for the OSPF area ID. Simple, I will say area, I keep the backbone, press enter. And same stuff I have to do for the other networks as well. So one is 10, and the other is 13, and the other is 12, right? So let's do it for 10, and then you can say 12, okay? And then see the links are coming up, and then you can say 13. Okay, like that. Simple. Now this will be a task for you. In this way, you can actually go to each of the routers and you can actually give all this commands, starting with the router OSPF, using the wildcard mask, and you will see the loading will be done. And then you check out the show commands and find out if they actually work. They will definitely work, because that is also one way of configuring the OSPF on router, and that's a preferred way because it's easier. You don't have to go to each of the interfaces and say IP OSPF and all that. You can directly go to the router and just say router OSPF with the process ID, and just give on the networks with the wildcard mask and the area, and you're done. A simple way, right? All right, with that, we came to the end of the OSPF lab part 1. Hope you enjoyed it. Meet you in lab part 2. Thanks for watching. Cheers. Welcome to OSPF lab part 2. So in this lab, we are going to talk about the DR and the BDR election process, and also check out a few elements of the OSPF protocol. Now, the CCNA scope of the OSPF will be ending here with this lab. In the CCNP, we are going to take a deeper dive by finding out the kind of the areas in OSPF, the different packet states, and so on. Okay, so let's dive in. Let me pull out a few routers here. Let me pull out 2 of them, and let's have the connectivity done. Okay, just segment it like this. Okay, now let's go ahead and name it R1, and this will be R2. Let me give some loopbacks here. So loopback on R1 will be 100.1.1.1, and on R2 will be 200.1.1.1. R1 gig 0 interface will be 1.1.1.1. R2 gig 0 will be 1.1.1.2. Cool. So let me go ahead and first of all configure the routers with this loopbacks and IPs, and also I will turn on the OSPF on the routers. So let's go to R1 first. Enable config T, host is R1, and then interface loopback, IP address 100.1.1.1. I will keep it /24 255.0. No shutdown because it's a loop back, and I will say gig 0/0. Now let me add the IP there, 1.1.1.1, 255.255.255.0. No shut, and we are done, right? Now I will enable the OSPF on loopback 1. Command is IP OSPF and followed by the process in a number or the ID, and area I will keep it 0. Process is 100. Similarly, I will go to interface G0/0 and make it OSPF enabled. All done. Now let me come to R2 and do the same there. Load the configurations and also ensure that OSPF is turned on. Config T, interface, loopback 1. IP address, here it should be 200.1.1, followed by 255.255.255.0. And interface, gig 0, and IP address 1.1.1.2, 255.255.255.0. I will give a no shut here, and we are done. Now I'll be turning on the OSPF. IP OSPF process 100 and area I will give it 0. And let me go for interface gig 0. Again, same command, and we are done, right? Okay. Now that we have enabled, let me just explain to you what is a DR and what is a BDR. So let's go with the definition first, and then I will show you with the help of a topology. So DR stands for designated router. Okay. Now, DR, when you turn on the OSPF in a cluster, let's say 5 routers, 10 routers, whatever, then out of the number of the routers in the OSPF group, one will be selected as the DR and one will be selected as the BDR. So when you select the DR, the router or the time taken to elect the DR or the designated router will be 40 seconds, which is called the wait time. Now, the election process, first of all, it will check the priority ID, okay, which is by default 1 for all the routers. But again, if the priority is higher, like the highest one with the router will be becoming the DR. If at all the priority is a tie or it's a match for all, like let's say like default 1 for all the routers, then it will check the highest router ID. Okay, that is how the DRs are being elected. Now, when I talk about BDR, that stands for backup designated router. Okay, and here also it's the same. However, it is priority. It will check, and it will be second highest. Okay. Similarly, when it checks the router ID, if priority is a tie, then the router ID will be second highest. Now, your question will be that once we select the DR and the BDR, let's say within a group of 5 routers, okay, then what happens to the other 3? The other 3, the remaining of the cluster will be known as DR only, which is designated router only. So think of it like a team of players, and the DR will be the captain, the BDR will be the vice captain, and the DR only will be the team of players. So now let me go ahead and quickly check what is the DR here. Very simple. I will go to R1 and I will go for do show IP OSPF. I will find out the neighbors, enter, and the neighbor for R1 is 200, which is fine. It shows here as full BDR. That is not correct. It should be showing as full DR. That's a fault of the packet tracer, because I probably would not have exited the packet tracer for quite some time. So it has taken some older configuration there. I'll do one thing. I will just reload the routers and it will come back to the proper state, and you will see what is the DR and what is the BDR. Okay. However, the point to be noted here is that for the production routers, please do not go ahead and reload the routers. It's only for the emulation that I'm doing it here. So I will first of all save the configuration to memory, do WR, and then I will say do reload, and that will reload the routers. Confirm, yes. Same thing I will do for the router 2 as well. Sometimes in the simulations you will be having some kind of problem, especially in these kind of the cases. You can always go ahead and you can always ensure that the routers are reloaded, and you save the memory, and you will see that they will you know come up with the proper configs. Okay, while it is doing that, I will just go ahead and I will explain to you what exactly is the concept or the reason for a DR and a BDR. So let me pull out some routers. Let's say 1, 2, 3. Okay, let's put out 3 only here. And let me just take a connection. Okay. All right. And this one. Okay, that's done. Now let's say that in this particular topology, let me pull out a marker here quickly. Let's say this router has got a X network connected. Now, if all the 3 routers are in the OSPF group, then you know by now that the network tables or the routing tables will be shared, right? The information will be shared, and we have seen how the hello packet works, how the DBD works, and so on. So if there is a X network which is connected to this router, it will automatically be plugged in to router 3 and the router 4 routing tables as well. Now, if there is a problem with the X network, like it's being unplugged or taken off or disabled or gone corrupt or something, if it's gone off, it's dead, then this particular router 2 will be sharing that info with all the guys. Like it will share with router 3 that, hey, the X is down, and router 3 will know that, and it will immediately take off the X from the routing table. And once router 3 does that, it will again push that info to router 4 that, hey, X is down. Okay, and router 4 will be also taking off the X from the routing table. Now, point is that this router 2, it will share the info with R3 and R4 in the beginning. R3, once it gets that, it will again flood it to R4 and back to R2. R4, like once it gets it, it will flood it to R2 again and back to R3. So all the routers will be flooding the network with the packets updating each other. Very similar to what probably we have seen in the layer 2 broadcast storm, and we stopped that with the help of the spanning tree protocol, right? Now here we do not have a spanning tree protocol. Here what we have got is that there is an election process, and the OSPF group says that once you turn on the OSPF, it takes like 40 seconds for the group to elect a DR and a BDR. Now DR stands for the designated router. Let's say this guy becomes the DR. Okay, and this guy it becomes the BDR. Okay, probably I have to add some more routers there to make it more descriptive. Let me go ahead and add a couple of more routers there, maybe one more here. Okay, uh, okay, so now what happens is that, and let me just connect these two guys as well. uh, okay, so now what's happening is that if I go ahead and make this particular router as the DR, let's say the process starts off after the OSPF is turned on, and in the election process, router 3 is the DR and the router 4 is the BDR. Then what happens if the X network goes down here? It will inform the DR and it will inform the BDR. That's it. It will not flood through all the interfaces. It will just keep the DR and the BDR informed in one packet flow. And once the DR knows that, it is the responsibility of the DR that the DR will be sending out the packet to all the routers and inform them in one shot, to this guy and to this guy and back again to this guy and this guy and all that. So it's just a two-step kind of process. Any network changes happen, that particular router will be pushing that information to the DR and the BDR with the help of the multicast group, right? It will not directly go to the IP, it will go to the 224.0.0.5 or 6. And the DR, once it knows that the DR will be taking the step 2, it will just update the information to all the routers in one shot. So there is no flooding of the packets. There is no having a chance of having the network performance going down and so on. So that is the concept of your DR and the BDR. Okay. Now, by now, the routers would have reloaded. So let's have a check now who is the DR and the BDR. So enable, and I will say show IP OSPF neighbor. And you will see 200 is the neighbor of R1, and it's a full DR designated router. Like I said, the DR will be checking the priority ID first and then the router ID. The priority ID by default is 1 for all the routers. Okay. Now, if it goes to find out the router ID, the router ID is the highest network ID, and the loopback will be beating them all because that will supersede all. So if this is 100, the highest one is 200. That's a loopback. So 200 will definitely be the DR, which is right now here. And the rest, this is the next hop to reach the 200 from R1, right? So similarly, if I go to R2, let's check out if that is the BDR or not. And let me just enable. Okay, config T, and I will just change the host name to R2. Do show IP OSPF neighbor, and you see it is BDR. My neighbor is 100, and that is the BDR, right? Very simple. Now, one more thing I would like to show you is, let's take you through a few of the elements of OSPF. Yeah, I will show IP OSPF, and I will say interface gig 0/0, right? Let's check out what is there. Press enter. Now here we have gone through most of them, but few are remaining. So we know that the process ID which we selected, that is showing up here as 100, which is up to your choice to select a process ID. Router ID of R1, that is 100.1.1.1. Okay, that is a loopback interface. Network type. Now what is this? Let me quickly take in a annotation here. Okay, network, when it comes to OSPF, first one is called P2P. There are 3 types. One is called the P2P, like point to point. And if I talk about point to point, then it is basically serial connection, right? Serial connection. And we also know that in the serial interface, there is no MAC address. So we really don't have to bother about the ARP, right? Second one, the second type of the network is broadcast. Broadcast is Ethernet connection, okay, which is right here, okay, and that's why it is showing us broadcast. That is router 1 to router 2 connected through a Ethernet, fast or whatever. And last one is called non-broadcast, which is beyond the scope of CCNA that you will learn in your CCNP. Okay, so these are the 3 kinds of the networks in OSPF. Let me just go ahead with the other options. Cost is 1, because cost, we know the formula of cost is what? 100 by bandwidth. Now, if here we are using the fast Ethernet, then it's 100 by 100, right? 100 Mbps. So 100 by 100, which is the bandwidth, that is 1. What if it's a serial? Now, serial, we know if it's a T1, then serial, we know that the connectivity speed of T1 will be 1.54 Mbps, right? In that case, the cost will be 100 divided by 1.54, which will come close to 64. And you see the huge gap, right? One is called only 1 and one is like 64. So definitely your 1 will be the preferred choice. OSPF always goes with the least cost. Okay. What else is there? This is telling you priority 1. Like I said, priority by default is 1 for all the routers in the OSPF. Okay. So though the first choice is like priority, it might be 1, and that's why the DR and the BDR, the process goes for the next step, which is the router ID. Designated router DR, that is 200.1.1.1. We know that, right? And the interface address of that is 1112. If I want to reach that, I have to go through 1112. Your BDR is this particular guy, which is 100.1.1.1. That is the router ID, and the interface address is 1.1.1.1, right? Now, the other part is about your hello, dead, and the wait. Now, what is hello, dead, and the wait? So let me just probably go back to the diagram here. Yeah. Now, hello means that if this is my router R1 and this is R2, okay, every 10 seconds, the hello will be sent out from R1 to R2, okay? And if by the 40th second, R2 is not going to respond back to R1, then R1 will think that R2 as a neighbor is dead, and it will remove that neighbor from R1's routing table or the neighboring table. Okay, so 40 means 10, 10, 10, and 10. 4 times, again, no response, which means immediately from R1, R2 will be taken off because it thinks R2 is dead. What is wait time? Wait time is the moment you enable your OSPF on the routers, then it will take 40 seconds to elect the DR and the BDR, and that is called wait time. Okay, let's see what else is remaining here. Yeah, I believe we have done with all the options of OSPF which are in scope of CCNA. We'll quickly show you a couple of things here. 1 second. All right, let me just remove this and okay, take this off. All right, and let me use the simulation. Just would like to show you the OSPF hello packet and the OSPF how it works out. So show all, I will just choose the OSPF protocol here, and I will go to R1, and there I will type in ping 1.1.1.2, right? Press enter, and let's come back here. Let's see what's going on there. So of course the OSPF is going. Let's see how it looks like. So OSPF is a layer 3 protocol, right? 89 is the IP there, and you will see that IP header, it's showing up. The source IP is 1112, okay, which is basically coming back from R2 to R1. Let me go to R1 first, and then probably from here we can check it better. Yeah, the source IP is 1.1.1.1. The destination is, see, the destination is not going to 1112, though we pinged it. The destination is going to the multicast address 224.0.0.5, and that's a hello packet, right? Ethernet 2 header information is right here. Now, if I go to outbound PDUs, you will basically see your Ethernet frame here. Okay. Below that, you will see your IP header. IP header is showing about your source IP and your destination IP. Your protocol will be 89. That's the incorrect thing in packet tracer. It is not 59. Your TTL is showing up here. And if you come down more, you will see the OSPF hello packet. Hello packet will be showing you the router ID, the area, which is 0. And if you come down more, you will actually see the network mask is showing up here. And you will see the interval of the hello packets. We know it's 10 seconds. A router dead, that is 40. DR is 1112, how to reach that, and the BDR is 1111. So, and your neighbor will be 200.1.1.1. So that's how the OSPF header looks like. Okay. In your CCNP level, I will be sharing you one session on IP header, TCP header, and the Ethernet frame with all the details, along with packet tracer and a network analyzer tool that's called Wireshark. It will be simple to understand the checksum, the flags, offsets, and so on, and have a detailed view about the IP header and so on. Okay. Right now, it will not be in the scope of the CCNA. So in CCNP, in the beginning itself, we will go through that. All right. With that, we came to the end of our OSPF Lab 2. I hope you enjoyed it. Thank you for watching it. Cheers.